Hi, in this video, we're going to have a look at one of the more complicated rules, I suppose, of differentiation, and that is the product rule. It's one of those things that you're just going to have to practice and practice until you get it right. So you can see that I've got the product rule written here. So if we have a function that can be written as the product of two other functions, and remember, these are like mini functions. So it could be two linear functions like 2x minus 3 and 3x plus 1 or something like that, then the derivative is given by this rule here. And I've broken my own notation rule really here by just to simplify what it looks like. So I've got here, if f equals u times v, then f dash equals u dash v plus uv dash. So that means find the derivative of the first part and multiply it by the second mini function, and then add to it the first function multiplied by the derivative of the second bit. And that's it. That's the product rule. It can be proven. You don't need to prove it. You just need to be able to use it. In your information sheet, you'll see that the product rule is written here in a slightly different order. They put this, I put this bit first, and they put it second. We're going to do quotient rule next, and I change the order of these because then it's just a matter of adding or subtracting the same pair, I suppose, if we switch these over. And of course, we can change the order of addition without any problem. And you can see with the UV notation, they've got v du by dx plus u by dv by dx. So, that's just the way it is worked out on the information sheet. And this is the way I do it. So what I'm going to take you through in this video is I'll take you through a few samples of the product rule in motion, just using some simple examples to start with, and then some more complicated examples. And in the second video, I'll go through a couple of fairly intense examples to try and give you a sense of how to go it. So if you have a look at slide 2 there, example 1, we have this idea of two mini functions. We have y equals 3x plus 1 multiplied by x minus 2. And if you're finding the derivative the normal way, in inverted commas, the normal way, then we would have an expansion first of all, done that in blue, and then I'll just find the derivative. Now let's have a look at how that works under the product rule. So the two mini functions are 3x plus 1 and x minus 2. They're the two functions. So I'll leave it zoomed out so you can see them both at once. So I identify u as the first function, so u equals 3x plus 1, and straight away I find the derivative of it, so u dash, which is equal to 3. Yeah? Then I write down v, and v is equal to x minus 2, that's the other mini function, and v dash is equal to 1. Okay, so there's my my pairs of functions there. And effectively what we're going to do is we're going to multiply these two together, that's u dash v, and add them to uv dash. So I put these brackets around them to pair them up. All of these visual reminders means as I'm working on my solution, I am giving myself little visual cues so that I don't make mistakes effectively. Do you have to do it? Of course not, but it makes a lot of sense too. So dy by dx is equal to, looking at the inside, that's 3 times x minus 2, plus, and then looking at the outside, that's 1 multiplied by 3x plus 1. Now that's equal to 3x minus 6 plus 3x plus 1, like so. And then if I simplify that a little bit further, I have dy by dx is equal to, let's have a look now. I need to zoom it out a little bit more. There we go. We've got 3x plus 3x is 6x, and we've got minus 6 plus 1 is minus 5. And surprise, surprise, the dy by dx by the product rule is exactly the same as the dy by dx, simply by expanding and using the power rule. So why would we use the product rule? We wouldn't. If it is already quite a straightforward process just to expand and use the power rule, for goodness sake, do that. That would be a much more straightforward way of doing it. So this is just to illustrate that the product rule works, and there'll be plenty of examples where it's not more straightforward to do that. Let's have a look at an example of that now. Okay, so example 2. To expand this by normal means first would actually take a fair bit of work. And perhaps we don't even need to, well, let's just go through it. By using the product rule, I would start off with u is equal to 3x squared plus 2x plus 1. And therefore u dash is equal to, just using the power rule, 6x plus 2. V is equal to 2x squared minus 3x plus 1. V dash is equal to 4x minus 3. There's the inside, there's the outside, and we add them together for the derivative. F dash of x is equal to, let me see now, inside, so that's 6x plus 2 multiplied by 2x squared minus 3x plus 1 plus, multiply the outsides there. So we've got 4x minus 3. I'm just putting the smaller term first, or smaller expression first. So 4x minus 3. Good if I could read my own writing, isn't it? Multiplied by 3x squared plus 2x plus 1. And that's basically done. That is now, the derivative has now been found. And so we can leave it at that, really. If we were told to simplify it to a single expression like that, we could then expand it if we had to, and then collect like terms and all that kind of stuff. But you don't really have to unless you're told that you must do so. So simplification maybe by expansion, but only if you think it needs to be done. Okay, let's have a look at example 3. D by dx of e to the power of 2x times by ln 2x. So we've got the product rule there. I didn't say this at the start, but product means multiplication, remember? So the product rule, we've got u and we've got v. Same process. U equals e to the 2x. U dash is equal to 2e to the 2x. Yep, so that's just a very simple chain rule. Derivative of 2x is 2. The derivative of e is just e to the whatever x. Okay, v is equal to ln of 2x. And so v dash is equal to, again, find the derivative of the whole thing, which would be 2. Find the derivative of ln of 2x, which will be 1 on 2x. Find the derivative of 2x, which is 2. 2's cancel out. As I've said in the previous video, if it's ln kx, the derivative is just 1 on x. Okay, so therefore, dy by dx, it's already in that format already, so I don't need to write that again. There's no y. That would equal 2, inside, then outside. So 2e to the x multiplied by ln 2x plus, looking at the outside, e to the 2x multiplied by 1 on x, which would be the same as saying all over x. Now, if you wanted to, you could then make it a little bit simpler by finding a common denominator. So that would be 2x e to the x ln 2x plus e to the 2x all over x. Can you see the difference there? The difference is just I've multiplied this one by x to find a common denominator of x. So x on the top there. And then one more step, if I really wanted to. I can't guarantee that this is anything particularly better, but nevertheless it is there. E to the 2x is a common factor there. Just realised I didn't put 2's here when I should have. E to the 2x is a common factor there, so that would leave me with 2x ln 2x here plus 1 all over x. I'm not confident that's any better than, say, this line here, but just giving you an example of how your algebra skills can be used if necessary. Okay, example 4, y equals cos x times sin x. We have u is equal to cos x, and therefore u dash is equal to negative sin x. V is equal to sin x. V dash is equal to cos x. Inside, outside, put it all together. The y by dx is equal to the inside, which is minus sin x times sin x. That'll be negative sine squared x. Remember, that means sin x times sin x. And then the outside is cos x times cos x. So that's plus cos squared x. And we might just want to tidy that up slightly if you like to go. That's cos squared x minus sine squared x. And I don't think that can be simplified any further, even though it feels like it's really similar to the Pythag identity. Cos squared plus sine squared equals 1. I just don't think there's anything we can do there with the skills that we have got anyway. So we'll leave that there. Example 5, f of x equals e to the power of x sine x plus cos x. Now, I guess the important thing to see here is that this is actually three functions, of course. These are the two that are multiplied together, and this is just another third function, which we're just going to treat as a separate part, really. So kind of, we've got this as u, this is v, and this, we just deal with as we go along. So we've got u equal e to the x, so u dash is equal to e to the x. V equals sine of x, v dash is equal to cosine of x. And so we have f dash of x is equal to, inside then outside, so we've got e to the x sine of x plus the outside, e to the x cos of x. And then we just need to put in that extra function there at the end there, which is the plus cos of x. And the plus cos of x would be minus sine of x, like so. So that would be basically it. I guess you could technically maybe factorize out the e to the x for these two, or factorize out the sine of x for these two. I can't really see anything that would allow factorization to occur any more simply. So there you have it, 5 different examples, all of them using your different basic fundamental derivatives that we've looked at, the power rule, the trigonometric ones, e to the x and ln x, and it's just mashing them all together with this quite simple rule, I suppose, which is that f dash is equal to u dash v plus uv dash. Okay, in the next video, I'll go through a couple of more complex examples, but hopefully that's enough for you to sort of see the process where we just break it down into small bits and then put it all together in order to solve our problems.